In this lecture, we'll discuss about series LCR circuit. So I have already drawn the figure for this series LCR circuit. You must notice that I have not applied any AC source across this series LCR circuit. All right. So why we are studying this? We want to study the analogy of this series LCR circuit with what we learned in the previous lecture, which is our mechanical harmonic oscillator with spring constant K, mass M, and damping B. All right. Now remember here, we are not forcing this system with any kind of periodic force. So that's why we have not applied any kind of AC source across this series LCR circuit. So the first thing we want to find is the differential equation governing the flow of electric current through this circuit. So we know the potential difference across the inductor is given by, let's denote it by VL. It is given by L di over dt. It's the rate of change of electric current flowing through inductor. The potential difference across or potential drop across resistance is given by I times resistance R, and the potential difference across capacitor is given by Q, which is the charges, and C is the capacitance. Okay, so by using this particular equation, we are going to find the differential equation for the series LCR circuit. So if you notice here, we are not applying any kind of external AC source in this particular circuit. So sum of these all potentials must be zero. So what we get here, let's write it down. So if I sum it out, I get L di over dt plus I times R plus Q over C equals to 0. All right, but now if you look at this equation here, so you have the differential term for this current, you have this current here, but you have the charges here. So if I write the relation between this electric charges and current, so I can write this down. So actually our electric current is a rate of change of charges. So I is dq over dt. So if I put this particular expression for this I and this differential equation, what do I get here? So L. So di by dt will be second derivative of q with respect to t. So it is d2q over dt square. Plus I can be replaced. I'll write R, which is a resistance. I can write this as a dq over dt plus q over c. I'll write it as separately 1 over c times q is equal to 0. So I get the differential equation for the charges in the circuit for this q of t, and see the dependence of q over time here. So this q charges in a circuit is a function of time, and this is governed by these constants: inductance L, resistance R, and capacitance C. So if you notice this particular differential, what we got for the series LCR circuit here, this is quite analogical with what we have already studied, which I have already written here. This is mechanical harmonic oscillator with spring constant K, mass attached M, and damping with a damping constant B. So this is quite analogy, right? So here you have second derivative of Q, second derivative of X, first derivative of Q, first derivative of X, the term X itself, the term Q itself, right? So let us write down certain analogy with this by comparing these two differential equations. So let me write the analogy or comparison here. So what we have here in electrical circuit and what we have here for this corresponding term in our mechanical system. So let's see here what we have here. So in mechanical system, this basically this differential equation is for the displacement x of t. So here in electrical system, we have the differential equation for the charges flowing through this circuit. Okay, so if I differentiate this particular thing, so this is dq over dt. So dq over dt is nothing but the electric current flowing through the circuit. And if I differentiate this dx over dt here, I'll get the velocity. So the velocity in a mechanical oscillator is analogical with the electric current flowing through electrical circuit. So next, if you compare the coefficient of the second derivative term here, we have the inductance here, we have the mass here. So in electrical circuit, inductance is equivalent to mass of mechanical system. If you take out the next term, the derivative, first derivative term, the coefficient of first derivative term in electric circuit is resistance. Here we have B. B is damping. And if you see the coefficient of Q itself, we have here 1 over C. And here we have this spring constant K. All right. So if I compare this M basically this term, this M term in mechanical, mass term in mechanical, this provides the inertia of the system. So in electrical circuit, my inductance is going to provide me the inertia. Next, B in a mechanical system is providing the damping. Damping, what does damping do here? So damping basically tries to die out the oscillations in the circuit. So similarly, the oscillations in this particular charges while flowing through the circuit are damped out by this resistance. So this is quite similar to damping. So in my electrical circuit, this resistance will be providing me the damping. All right. And this is kind of restoring force, because in mechanical system, I have the K term. This K term is basically restoring force, right? So here my capacitance will try to restore the electric charges in the circuit. So this is what? So this, the first thing which we have studied, mechanical oscillator, this expression for the series LCR circuit, the governing differential equation for the series LCR circuit looks quite similar, exactly similar to what we studied for the mechanical harmonic oscillator. So we know the solution for this particular equation, right? So remember, first of all, we are not forcing this function, forcing this system to oscillate with certain external force, which is periodic in nature. So that's why here also in electrical circuit, I'm not applying any kind of AC source, which will be fluctuating with certain amplitude, right? So let us not worry about the forcing function right now. So initially, this equation represents in mechanical system the damped oscillations. This equation is for damped oscillations. So here also, let's study the damped oscillations in our electrical system. So let us write down the differential equation for this series LCR circuit without any kind of external source. So let me write it down. So here, so I can write this out as L over d to q over dt square plus R times dq over dt plus 1 over c times q equals to 0, and there is no forcing here. So again, for solving this particular differential equation, remember in damped oscillation for mechanical system, we have divided this entire equation by mass M. So similarly, if I divide this by inductance L, I get this differential equation d to q over dt square plus R over L. So this is dq over dt and plus this is 1 over LC times q equals to 0. Now, if you compare this with the differential equation, what we got in mechanical system, it will look like this. dt square plus, there for this resistance, we had B over M dx over dt. And for this plus, we had this K term here over mass M times X equal to 0. So from this, what we took here B over 2M, which is equal to lambda. And this K over M is the square of natural frequency of the system with which it will keep on oscillating in presence of, in absence of damping. So similarly, I will write these terms here. So if I look at the coefficient of this dq over dt, which is R over L, let me replace by this 2 factor here, which is lambda, similar to this, exactly analogical to the mechanical system. And if I compare the coefficient of Q, it is 1 over LC here, which is equal to square of natural frequency of this series LCR circuit. And you must have seen this in your 12th standard, right? Omega naught square is equal to 1 over LC. So this is what we have obtained for series LCR circuit by putting the capacitive inductance and capacitive reactance and inductive reactance equating, we have got this particular relation. And here, just by solving this particular differential equation for series LCR circuit, we're able to find the natural frequency of the series LCR circuit, which was the same as what we studied in the AC circuit part, right? So, all right, then let me write the solution for this. So what we write down as a solution for this x of t, depending on the conditions, right? So what are the conditions? There are certain conditions on this. So this lambda square, the first condition is lambda square is less than omega naught square. Okay, so let me write these solutions. So in that case, I'll be getting this C1 times cos omega naught t plus, sorry, omega t plus C2 times sine omega t. All right, because we have got this expression. So let me write down the solution for this mechanical system here. So this solution looks like I have one constant like minus lambda plus square root of lambda square minus omega naught square, and alpha 2 is minus lambda minus square root of lambda square minus omega naught square. And from these two, I have written my solution for this x of t is equals to some constant times e raised to alpha 1 t plus some another constant times e raised to alpha 2 times t. And depending on the case, if my lambda square is less than omega naught square or it is equal or greater, we had three cases. The first one is underdamped, in which case lambda square is very less than omega naught square. So in that, this square term will become negative, so it will go into complex, and this will be multiplied by this will be oscillating term, and it will be multiplied by with certain term which is decaying with respect to time, exponentially decaying with respect to time, and multiplied by with some another constant. Okay, so you cannot there is no need to take this out constant because you have already taken these two constants, and you have, as this differential equation is second order in nature, you need two conditions to solve this particular equation, or to find out these two constants you need two initial conditions, right? So let's not worry about that solving part of differential equation again. So if you have this lambda square is equals to omega naught square, so this is underdamped oscillation. So this is critically damped oscillation. So for this, we have got the expression like C1 plus C2 times T e raised to minus lambda times T. And for overdamped system, I'll simply write C1 e raised to alpha 1 times T plus C2 e raised to alpha 2 times T in case lambda square is greater than omega naught square. This is overdamped system, right? But usually in series LCR circuit, we end up with finding our system to be underdamped, right? So we are not bothered about these particular two conditions based on lambda square value. So let's not worry about these two solutions in which we get critically damped system and overdamped system. Generally in series LCR circuit, we end up having our system to be underdamped. So what do I mean by underdamped? My energy, as there is a damping in the system, my energy is going to die out with respect to time, but it will keep oscillating while doing that particular thing, right? So we have already seen that graph. So it will have certain amplitude, and this amplitude will keep decaying because there is an exponential decay term here. And at the same time, we have this periodic function, so it will keep oscillating. All right then. So on the similar basis, if I write the differential solution for this differential equation for this electrical circuit, so what I can write here? So I'm assuming that my system is underdamped system. So this solution will look like this. E raised to, again, minus lambda times T multiplied by some constant C1 cos of this omega T plus C2 sine of omega T. C2 sine of omega T. So this is the solution, assuming that my system is underdamped system, what we have got for the mechanical oscillator, right? So again, lambda thing here varies like this because here lambda, remember here lambda is R over 2L, and this omega would be, I'll write this omega square, as we have considered this omega naught square is greater than lambda square. So it would be omega naught square minus lambda square. All right. Now suppose this is what? So if I consider here, suppose there is no damping at all. So special case of this particular solution, the first thing what we studied here, we don't have any kind of external AC source. So what I mean by that, so there is no external forcing, periodic forcing in mechanical harmonic oscillator. And same analogy in electrical circuit, I don't have any external AC source. So it means that it is damped oscillations, and we have got the similar expression for the Q of t. And if you want to find out the current flowing through circuit, you can simply take the derivative of this Q with respect to time, and you'll end up with finding the current flowing through circuit. That is not the problem here. All right. Now we have studied this damped oscillation. Now in damped oscillation, suppose there is no damping. So special case here, no damping. So what happens here? Suppose no damping. So what is meant by no damping here? So in electrical circuit, the damping is represented or taken care by the resistance R. So no damping means I don't have any kind of resistance in my circuit. So my circuit will look like, so I have this circuit in which the first thing, I don't have any kind of external source. So I just have this inductor here, which will be directly connected to this capacitor. Now, suppose this capacitor is initially charged. This is capacitance, this is inductance. There is no resistance. So that's why I'm calling this as a no damping. So this is exactly equivalent to having mechanical system with a spring and mass without any damping. And you know this, if you just have this mass and the spring, so it will keep oscillating between certain amplitudes without that amplitude being decaying out, right? So similarly, you must have studied this beautiful phenomenon of LC oscillations. So what happens here? So suppose this C, this capacitor is initially charged, so it will have certain kind of electrical energy associated with this capacitance due to the presence of charge because it is fully charged. Now, as time progresses, it will try to give out certain electric charges and try to establish certain current flowing through this particular circuit. And when this current is flowing through the particular circuit, now my electrical energy associated with this capacitor will be transferred to certain amount of magnetic energy associated with this inductor. So what is happening here? My electrical energy for C is getting converted into the magnetic energy associated with the inductor, and it will keep exchanging between this electrical energy and this magnetic energy. Okay, so when this capacitance entirely get discharged, the entire electrical energy is switched to magnetic energy associated with this inductance. Now again, this magnetic energy will keep starting this capacitor in opposite direction, and now this magnetic energy is now getting converted to electrical energy. So if I plot a graph over here, so suppose this will be the graph. So sorry for this. So you actually have this, suppose this is the energy, maximum energy. So one energy is going to decrease with time and another energy is going to increase with time and will die out. So this will happen at the same time, this at same time. So this is initial electrical energy coming down, 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 becoming zero. At zero, I have converted the entire electrical energy into the magnetic one, and again switching between them. So one is decreasing, other is increasing, so that the total energy remains constant because there is no damping, because there is no resistance. So basically in electrical circuits, this resistance is responsible for dissipation of energy, right? Because there is no energy dissipated in ideal conductor and capacitor, right? So whatever is responsible for the dissipation of energy in system, that is our resistance. And in special case, we have considered this resistance to be zero here. So I know the entire energy will keep oscillating and there is no decay or a loss of energy or dissipation of energy. So if I put this here, so if I put this R over here, if my R is zero, this lambda becomes zero. If lambda becomes zero, so this decaying term will vanish. And what I end up with having here, Q of T would be your omega. Look at the omega expression. Okay, so where is this omega expression? I'm not able to find it out here. All right, so it is here. So this omega, okay, here, it is here, right? So this omega, if my lambda is becoming zero, so if R equals to zero, then my lambda equal to zero. And if my lambda equal to zero, then this decaying term will vanish and my omega will be equal to omega naught. And if I look at the solution for these charges as a function of t, it will look exactly like C1 cos of omega naught t plus C2 sine of omega naught t. And you can combine this cosine and sine function together and you can simply write as A times some sine or cosine, depends what kind of trigonometry you use. If you put C1 to be equal to cos of some alpha or delta, C2 to be equal to sine of some delta, you can write this as a cos of omega naught t minus delta, right? So that I'll leave it to you. So you can write this as omega naught t plus certain phase angle delta. And this A is again amplitude with which it will keep oscillating, which is equal to C1 square plus C2 square. Now, this is not important for me. So what is important for me is the graph. If I look at the Q of t, how this charge is flowing through the circuit with respect to time, you'll look at this expression here. A, it's some amplitude, so it will keep oscillating between, let's say, plus A and minus A. And if you look at this function, this sine function is periodic. So let me start from 0. So it will keep oscillating between this plus A, minus A, plus A, minus A. And remember, there is no decaying term here, so it will keep oscillating between the same limits, plus A and minus A. That's why when you don't have a damping in your system, your energy remains constant. Your energy is not going to dissipate at all. So this is what happens. This is what happens in this beautiful phenomenon called LC oscillations. But again, I just want to wake you up that we don't have this no damping phenomena in practice, right? So that is not possible. So in mechanical system also we have seen that there has to be a damping. Even if you consider an example of simple pendulum, the motion of this pendulum will be opposed by the air drag itself. Though it is very small, but it is there. This B is not ideally, B can be hypothetically 0, but in practice B can never be 0. So similarly, in electrical circuits, these connecting wires, to make this circuit complete, this connecting wires will definitely have certain kind of resistance. And the inductor here, whatever we have considered, we called it as an ideal inductor, which means there is no internal resistance associated with it. But in practice, it is not possible. So in practice, we cannot have this resistance to be 0. So in any LCR circuit, I must have certain resistance, though it can be minimum, but it is there. It is non-zero. That is important for me. So I can have a small damping. And whenever I have the small damping, there will be energy dissipation through the resistance, which will look like Joule's law. It will keep on heating the circuit due to the presence of resistance. And I end up with energy dissipation or energy loss. So this is what we have studied in the mechanical harmonic oscillator, and this series LCR circuit is quite similar to mechanical harmonic oscillator. Now I'm going to connect certain kind of external source to the circuit, and let's see what happens here. All right, now we are going to connect external AC circuit across the series LCR circuit. So let's go into that. All right then. So now I have this resistance over here. This is R. So I have this inductance over here. This is L. I have a capacitor over here. This is C. And now I have certain kind of source over here, AC source. Let me denote this AC source. You can denote, this is AC, so I can, if I denote by E, this would be some E naught amplitude, let's say sine of omega t. So this is AC. Obviously, you have to be periodic in nature with certain amplitude. So I'm taking this E naught sine omega t. Now, if I write the differential equation for this particular term, so the potential drop across this inductance L di by dt. So I can write this out as d2q over dt square, as usually written, as we have already previously seen. So this I times R I can be written as dq over dt plus q by c, 1 over c times q. And now this potential drop must be equal to the externally connected AC source, which is E naught times sine omega t. And if you look at this equation, this exactly looks similar to m d2x over dt square plus b dx over dt plus kx equals to some external force which is periodic in nature, and it is periodic with certain frequency omega. So this is quite similar, right? So here We have already seen the analogy between these terms. Here, our external force F equals to F naught sine omega t. This is analogical with external source for EMF, which is E equals to E naught sine omega t. And now, as these differential equations looks exactly similar, the solution has to be exactly similar. And we have seen the solution methodology in the last lecture. The solution will be comprising of two parts. So if I write this, the solution for this x of t again here, this x of t will be comprising of xh of t plus xp of t. So this is homogeneous part. This is, let me write this down, homogeneous part, and this is particular solution. So this homogeneous part, this depends on initial conditions for which you'll be solving this differential equation. And this will be kind of our damped oscillations, which as t tends to infinite, our xh will vanish or decay out or die out, right? So as t times tends to infinity, this is approaching to zero. So eventually, with respect to time, this homogeneous solution is going to die out. And what remains is this. That's why this solution, we call this as a transient solution, which is basically time dependent. And this, we call it as a steady state solution. Why steady state? Because it will keep oscillating. It does not have the decaying term. So it will have only oscillatory term, and it will keep oscillating forever with the frequency of forcing function, omega, right? So it is called as steady state solution. So exactly the same way here, Q of t in electrical circuit, I have QH of t, which will be known as transient solution, And again, QH will tend to zero. This will die out as t tends to infinite, as time progresses. Plus, there'll be a particular solution due to the external forcing function, external AC source, and this is known as steady state solution. And our system eventually, after a certain amount of time passes by, our system will keep oscillating with this particular solution, right? So let me write down the solution for this xp of t. How does it look? It will look like some amplitude times sine of omega t minus some phase angle delta. And how to find out? We have already seen in the previous lecture, right? Okay, and so what is important here? This amplitude. This amplitude is important for us. This amplitude is given by what? This is f naught over m divided by, into the bracket. So first term is 2 lambda times m bracket square plus omega naught square minus omega square bracket square raised to half. And if you write the analogy here, this QP of t can be again written by some amplitude A times sine of omega t minus some phase angle delta. So if you look at the solution, my steady state will keep oscillating between these limits plus A and minus A, and with this periodic nature. And if I compare this here, so I have, instead of F naught, I have this E naught here. So I'll write this out, E naught. For this M, I have this inductance. Also I'll write L divided by, into the bracket, the first term, I have taken lambda again here. So this would be L squared plus this omega naught squared minus omega square bracket square raised to half. So what is lambda here? So lambda is resistance over twice of inductance. And what is omega naught square here? Omega naught square is 1 over LC here. And if you compare here, so here lambda is B over 2M, and your omega naught square is K over M. So this is the thing. And you can, in this as well, you can combine this M with this. If lambda times M is B over 2, you can write this over here. So 2 lambda M would be B square. If you compare, if you put sorry for this. I have omega here. So I have mistakenly written this. I have omega here. Okay, so if you put the 2 lambda is b over m, and if you multiply with m into this, so you can end up by writing this expression in terms of b, k, omega, all these factors we have taken in the example itself, instead of writing in terms of lambda. That also we can see here. So let's see that here first. Okay, so let me write the amplitudes first. So amplitude for the mechanical system is f naught. Let me combine this mass over here. So this is 2 lambda omega square plus omega naught square minus omega square bracket square raised to half. Now, if you find the 2 lambda value, 2 lambda would be b over m. And if you take this m inside, it will go as m square due to the square root. So what happens here? So this 2 lambda omega, the entire square, and this will go as m square, so it will be multiplied by m as a whole square. This term becomes what? This 2 lambda is b over m. So this is b over m times omega times m bracket square. So m gets cancelled. So this is equal to b omega square. So this term will become b omega square. And what happens here? So this is like what? This is like what? Omega naught square. Omega naught square bracket square. So if I take this m inside, so it will be like omega naught square minus omega square times m, the entire square. And if you write this term, if you multiply this particular term inside, so this will look like this omega naught square is k over m minus omega square times m bracket square. So this will look like, if you multiply m here, is k minus m omega square bracket square, k minus m omega square bracket square. So I can write this as f naught over into the bracket. The first term is b omega bracket square plus k minus m omega square bracket square raised to half. Why I have written this down? Because in my system, I know the spring constant, the mass being attached, the forcing frequency omega, and the damping constant b. That's why I have particularly written like that. But that is not mandatory here, though. Okay, all right. And similarly, if I write for the electrical circuit, I have this, instead of this F naught, I have this E naught, amplitude of EMF being applied. Instead of M, I have this L into the bracket 2 lambda times omega bracket square plus omega naught square minus omega square bracket square raised to half. And if I write the analogy from this expression particularly, so I have this E naught here divided by into the bracket first term. B is the damping. Damping is provided by R, resistance, times omega forcing function bracket square plus this is K. K is 1 over C minus M is L. This is omega square bracket square and raised to half. So this is what I have directly written with by using our analogy with this electrical circuit here. Now, again, we're going to study certain special cases for this forced oscillations, because now we have applied external circuit, which is periodic in nature, right? So we have special conditions, and the first special condition, the only special condition what we study here is called as resonance. So resonance, when does it occur? So when my forcing function frequency is exactly equal to the natural frequency with which system oscillates. In that case, my amplitude of this solution. So in case of mechanical oscillator, it will be displacement, and in case of electrical circuit, it will be charge. So it will shoot up and it will increase. Okay. So when this omega equals to omega naught, if you look at this particular expression, so let me write the, we have it here. If you look at this particular term here, at omega equals to omega naught, this term will vanish again. So it basically means this second term will vanish, and you end up with only this term, this Q of t. Let's not write the Q of t, because I'm just writing this amplitude, because if I write Q, then I have to consider the periodic function as well. Okay, so this would be E naught over R omega. E naught over R omega. And this omega is actually omega naught. So this would be like this, E naught over R omega naught. So this is what system will have, and this would be the maximum amplitude of system. And in this case, in particularly when in case of resonance, there is no damping. If I don't have any damping, I don't have any damping. So in electrical circuit, what is meant by no damping? My resistance is 0. So in that case, this amplitude, maximum amplitude, will shoot up to infinite, and my charge will shoot up to infinite in electrical circuit. But again, I'll again repeat, practically this is never possible to have resistance equal to 0, because in circuit, the wires you are using for the connection, those will be having certain kind of resistance. So it is not possible for us to have 0 resistance in the circuit. So all the time we'll be having certain damping, and due to the presence of damping, my amplitude will shoot up, but that will never go to infinite. That will be having certain finite value. All right. So again, if I look at the graphs here, so if I plot this Q of t versus the frequency of, this is the frequency of external source which is being applied. So for certain frequency, my Q value will be having the maximum possible value. And again, it will come back to this, and this looks exactly symmetrical about this omega equals to omega naught, which is the natural frequency of system. Right? And again, as we have seen, corresponding to this omega naught, I'll be having maximum power dissipation. If I consider the half of the maximum power dissipation for corresponding that value of half of the maximum power dissipation, I'll be having two frequencies. Let me call it as omega 1 and omega 2. And the difference between this omega 2 and omega 1 is known as bandwidth. And based on bandwidth, we can define the quality factor of this series LCR circuit, and this Q factor will be defined as omega naught over bandwidth. And if my bandwidth is smaller, then this quality factor will be higher, and I can say that my resonance occurring in series LCR circuit will be sharper, right? So these all things which we already have seen in case of mechanical harmonic oscillator subjected to periodic forcing. So these all things will be similar here. All right. So that's why we have studied this particular series LCR circuit, which is quite analogical with the mechanical harmonic oscillator. So this is the beauty of mathematics. So if you look at the differential equation itself, so it is something like a times some d2, let me call this variable in general, d2y over dt square plus b times dy by dt plus c times y equals to, there is some periodic function. So let me call it as a d of t. This is periodic function. So this differential equation, if you look at this as a mathematics perspective, this is just a differential equation, and this has the same form for mechanical harmonic oscillator as well as electrical series LCR circuit. So that is the beauty of mathematics. That's why we have compared the electrical series LCR circuit with the mechanical harmonic oscillator. So that's why those two things are quite similar. So in the next part, I would ask you to go and see the AC circuits and see the beautiful phenomena of LC's oscillations. There you get to know the undamped oscillations. Your system will keep on oscillating between certain amplitudes, and there is no dissipation of energy. All those phenomena you can easily compare with the mechanical system. That's it.